Good
Yeah.
afternoon and welcome to my presentation. My name is Matic Ivančič and I'm a researcher in company Larrasoaña, which is part of Magi Scientific. Today I'm going to talk about the method for the detection of mineral dust concentration, which is based on measuring optical absorption of dust aerosols. So why to measure mineral dust? Mineral dust is important natural source of aerosols, which can strongly influence their quality and has an impact on global warming cycle with light absorption and scattering. Sand and dust storms are also mentioned in new WHO report published this year. The measurements and predictions of dust events are required by WHO guidance to take measure in time with aim to minimize the effect of dust to health. The Sahara Desert is a large source of dust and PM10 in general, and frequently it can influence the local air quality in Mediterranean and further north in Europe. To our knowledge, there exists no direct method to measure dust concentration locally and in real time. So the new method I'm going to talk about today was developed within the international project DNEP, where acronym DNEP stands for Detection of Non-Anthropogenic Air Pollution. Our company was responsible for project coordination, and we developed a method together with partners from Josef Stefan Institute, the Cyprus Institute, Institute of Environmental Assessment and Water Studies from Barcelona, Eurovisia, and Helmholtz Centrum from Dresden. Initially, the measurement campaign was planned for a period between February 2019 and July 2020, but we extended the campaign, and the instruments are still running on sites in Spain, Cyprus, and here in Ljubljana. To explain how the lab method works, we have to understand some properties of mineral dust first. Here we have a picture from electronic microscope. Several pieces of mineral dust can be observed here, and we could see also some black carbon was captured at the same time. So here is black carbon, and these bigger particles, bigger aerosols are mineral dust. The black carbon is strongly absorbing refractory elemental carbon, and it is an important marker for the anthropogenic air pollution. It is a consequence of incomplete combustion, and wildfires are the only natural source of black carbon. The light absorption on mineral dust is weaker than the light absorption on black carbon, which makes it difficult to develop a method to measure optical absorption only on mineral dust. Fortunately, we could take an advantage in the second property of mineral dust. Mineral dust is usually bigger than 1 micrometer. It is in so-called coarse mode, while the black carbon is usually smaller than 1 micrometer. It is in so-called fine mode. This fact could be also easily observed from this image. So the key for our method is to concentrate the coarse mode of our sols to enrich the mineral dust content in the sample. For this purpose, we developed the special size selective inlet with high volume virtual impactor, which I will explain with following slides. Firstly, here is a sketch of ordinary inlet without any site selection. Black carbon and mineral dust are mixed, and as I already said, the light absorption mineral dust is shadowed by black carbon. On next slide, here is a sketch of a high volume virtual impactor where we are using two different flows. Major flow is around 100 liters and per minute, and minor flow is 2 liters per minute. Because black carbon is smaller, it has lower momentum. Therefore, it's easier to change its trajectory. On the other hand, coarse particles are bigger with higher momentum. They are steering in initial direction with such setup. So with this setup, we are throwing away the fine mode aerosols with the major flow. So basically, majority of strongly absorbing black carbon is removed. With the minor flow, we are then sampling aerosols in coarse mode, which could be further analyzed. On the left, we have the inlet developed within the project. On the right, we have some laboratory results. The concentration efficiency is shown with the blue line. Average aerodynamic volume size distribution for, let's say, normal inlet is presented with black line. But because the concentration efficiency is bigger for bigger aerosols, we could see that the peak of the volume size is shifted to bigger aerosols, in this case of inlet with virtual impactor. We defined the enhancement factor, which is the multiplication factor that reflects the enrichment of coarse fraction downstream of VI. So the enhancement factor is the characteristic of our setup, and it was estimated to be equal to 11. To measure optical absorption, we used a talometer. It has dual spot algorithm, which offer us to compensate nonlinearities coming from loading effect in real time. It has 7 wavelengths, so wavelength-dependent optical absorption could be measured. Dust and black carbon have different spectral dependence of optical absorption. The absorption Angstrom exponent of pure black carbon is around 1, while mineral dust absorbs light more efficiently at lower wavelengths. Therefore, the lowest wavelength 370 nanometer is the most appropriate for the separation between the light absorption mineral dust and black carbon. And of course, if we want to transform the optical absorption to mass concentration, we need a calibration constant called MAC. So mass absorption cross-section. MAC for black carbon is well known. The MAC for dust will be determined at the end of the presentation. Here is our methodology. There are 2 retalometers, one with virtual impactor as inlet and another one with PM1 cyclone. With the talometer with PM1 cyclone, we measure anthropogenic contribution to local pollution, because black carbon is the only light-absorbing aerosol within fine mode. With the talometer with VI inlet, we are analyzing the optical absorption on coarse aerosols. But because the efficiency of VI inlet is finite, all black carbon cannot be removed from the sample, as we also marked in a sketch 3 slides ago. Anyway, we can correct the mineral dust light absorption estimation for mined black carbon in coarse mode sample with the enhancement factor, which I already said is the characteristic of our setup. So here is the estimation of optical absorption on pure mineral dust. We have to subtract the measured absorption on the instrument with PM1 inlet from the absorption measured on instrument with VI inlet, and we have to weigh the difference with enhancement factor. Finally, mineral dust concentration is estimated from the optical absorption with calibration constant MAC. Okay, so simple proof that our size selection is working is the color of the filter tape. Here we have 5 filter tapes with installed different size selective inlets from Ljubljana and Barcelona. All images here are slightly saturated to increase the visibility. On the left side, images are from, let's say, normal operation when the presence of mineral dust is not expected. All dots are black, also the ones from a talometer with VI. On the right side, we have pictures of filters sampled during dust event. On the tapes from instruments with PM1 and PM2.5 self-selective inlets, the dots are still gray because mineral dust is in coarse mode and is not sampled here. But the color of filter dots from instrument with VI are yellow, as it expected for mineral dust. We investigated filters collected during our campaign also into more details with helium-ion microscope. First, we have prepared the helium microscopic images for the filter tape from instrument with PM1 inlet. On both pictures, we could see a lot of microfibers, which is actually the structure of our filters. On the right zoomed image, the microstructure of black carbon can be also nicely observed. On the second slide, the helium microscopic images are shown for the filter tape from instrument with VI inlet. We can see again the microfibers as a structure of filter tape. The dust aerosols can be already observed in non-zoomed image on the left, and detailed structure of giant mineral dust aerosols on right side. If we zoom the right image further, we could find also a black carbon on the same image. You can see also a black carbon here and here. So this is just confirmation that the correction for absorption on black carbon is required if you want to use our method. Before we continue with the results, I must give you some information about uncertainties of the method. Taking different uncertainties into account, the overall uncertainty is estimated to 40%. And here we have the estimation of the MEC from 3 stations. On x-axis is measured optical absorption on mineral dust, and on y-axis is the estimated concentration of mineral dust. MEC value is 1 divided by the slope. Dust was estimated with 40% method in Barcelona and Ljubljana, while the dust events in Cyprus are too frequent for this method. Therefore, chemical analyses were used there for the dust estimation. The plot is in logarithmic scale because the dust is estimated along 2 orders of magnitude. You can see nice correlation, especially for higher concentrations, and some more uncertainty for lower concentrations, as expected. The common MEC estimated from whole data set was equal to 0.15 square meters per gram. We prepared the MEC estimation also for each station separately. You can see only minor differences between these stations, which confirm the overall usefulness of the method. For the station in Cyprus, we split the MEC calculation regarding the source region, the situation when the dust was coming from Northern Africa and the Middle East. So the dust from Middle East was slightly less light absorbing with a slightly lower MEC value. We can compare the MEC for dust with MEC for black carbon. So we can see that the ability to absorb light is more than 100 times higher with the black carbon. And these are the results of more than 2-year-long measurements. Here we compare the dust concentration with orange with PM10 measurement presented with blue. The station in Ljubljana and Barcelona are characterized as city background, while the Agia Marina in Cyprus is regional background station. On the left side we have time series, and the mass closure is on the right side. Ljubljana and Agia Marina, the dust concentrations are always lower than PM10 measurements. You could also see higher dust contribution during intensive dust events, like here and here. The mass closure for Barcelona is not so good. Most probably the reason is the complexity of the site. It is a mixture of urban pollution with possible local dust influence during the dry period. One benefit of the presented method is to study dust intrusion into more details with high temporal resolution. For example, we can check the situation from May 2020 in Cyprus. Air masses were advected to Cyprus from northern Africa with some detour over Greece and southern Italy. The concentrations of dust were not equal all the time, but aerosols were coming in waves. Maybe we can check another interesting event in Ljubljana from March 2020. We could see that our method underestimated the amount of dust in this situation. The same could be also observed on scatter plot here. In this situation, the dust was advected to Slovenia from Asia and not from Northern Africa, which is usually the case. The source region for this non-usual event was desert near Caspian Sea. The mineral and chemical structure is most probably different in this region. Most probably the MEC estimated from our other data was too high for this event, which led into underestimation of dust concentration with our method. We can conclude that the possible variability of MEC is the biggest drawback of the presented method. We showed it works fine for dust advection into Europe for known source regions. To summarize our talk, we developed a method to separate the natural and anthropogenic contribution to air quality. Method is automatic, offers us real-time analysis with high time resolution. We tested the method with more than 2 years long dataset. If you would like to learn more about the project, I would like to invite you to visit the project webpage, where the results are also published in real time. We started also a new campaign in Qatar this year. Just 1 week after installation of the instruments, very intensive dust storm happened. You can see it in a video on the left. The dust concentration exceeded 500 micrograms per cubic meter. Our instrument survived the storm without a problem. Qatar is also an interesting location because there is an interesting mixture of local white dust, reddish transported dust from Saudi Arabia, and strong anthropogenic local pollution. So I'm really looking forward to analyze the Qatar dataset. At the end, I would like to invite you to a presentation on Thursday morning. Balint will talk about the dust storms in Qatar. He's now a member of our team, but before he worked in Qatar for several years. And finally, I would like to thank our Ministry of Economic Development and Technology and the European Regional Development Fund for the financial support for the DINA project. And the most important, I would like to thank you for your attention with the postcard from Ljubljana. Thank you.
Thank you, Matic, for your presentation. Interesting working.
Thank you.
Are there any questions? One question, please.
I certainly welcome the extension of the MAGI ethalometer to mineral dust. My question is the center of attention, or the most vulnerable part, is the MAC, the mass absorption coefficient. It took 10 years to get a value for black carbon that everybody could agree on. Now it is much smaller than for black carbon, but my question is, what do you do if you have Saharan dust? Saharan dust in Morocco has a high load of hematite and magnetite, and is very intensely colored. Other regions are not. And so I'm asking, what is the previous work of calibration? How much effort has to go into calibration compared to measurement when you want to gauge or record the atmospheric load of mineral dust?
Okay, thank you very much for this very interesting question. Yeah, actually, I would say that I was quite surprised that we did not observe so many differences in MAC. But anyway, maybe we can study this into more details with more vector trajectories analysis and better identification of source regions for every event. But I think in general, we would get quite a good approximation in, let's say, in real time for what are the concentrations. And yeah, but if we want really detailed, we need to separate every event and found its source region. So I don't know in general, we can get a rote estimation, but yeah, for details, we have maybe to wait slightly longer to get better.
Okay. I check the chat bar. No, I don't see further question for you. Thank you very much. And then we can move to the next online presenter, Maria Gavrouzou, that talks us about a case study of aerosol cloud interaction and temperature inversions during dust aerosol episodes in the Mediterranean basin.
Good morning to everyone. I am Maria Gavrouzou and I am a PhD student in the University of Ioannina in Greece. Today I will present you a part of my PhD work with title Aerosol Cloud Interactions and Temperature Inversions during Dust Aerosol Episodes in the Mediterranean Basin. Specifically, we will discuss the case study of 16 to 18 June 2016. Here we summarize the methodology applied. As the first step, we determined the dust aerosol episode case, which is examined here, and is defined as sequent days with dust export over the Mediterranean basin. The determination of the dust aerosol episode case was done using a satellite algorithm, which is based on aerosol optical properties and is fully described in Gigas et al. 2016 and Gavrouzou et al. 2021. As the next step, we produced maps of aerosol optical depth and dust optical depth using MODIS and MERA2 reanalysis data respectively. We examined the synoptic conditions at 3 atmospheric levels at the surface at 850 and 700 hectopascal using data from NCEP-NSAR database. We also created the geographical distributions of cloud cover as well as cloud top properties using data from MODIS instrument. Later, we produced vertical cross-sections of temperature gradient and dust optical depth using vertically resolved MERA2 reanalysis data. And at the last step, we took wind direction and speed, temperature, relative humidity, and dust optical depth horizontal cross-sections at specific levels, which were indicated by dust optical depth vertical distribution cross-sections. Here we present the synoptic conditions one day before the episode, and what we observe is that at both the examined levels of 850 and 700 hectopascal, a shallow trough is observed over the Iberian Peninsula and northwestern Africa in conjunction with a slight ridge over the central and western Mediterranean basin. Here we present the aerosol optical depth and dust optical depth geographical distributions on the same day, and what we observe is that low values are observed over the greatest part of the Mediterranean basin, except for parts of North Africa and Middle East. Here we present the cloud fraction derived by MODIS instrument for liquid and ice clouds, as well as for their combination. What we would like to highlight at this slide is that no clouds exist over the greatest part of the Mediterranean basin, except for some liquid clouds over the northern parts of the basin. On this slide, we give the atmospheric circulation on the first episode day, And what we observe is that the trough over the Iberian Peninsula and northwestern Africa is now more deep at both the levels of 700 and 850 hectopascal. The ridge at 700 hectopascal is now sharper and moved eastward, while a low pressure system is formed over the Western Mediterranean basin at 850 hectopascal. Here we present the AOD and AOD anomaly distributions. As we can see, dust is exported from northeastern Algeria through Tunisia and central Mediterranean basin. Missing values are indicated with white shaded areas, and AOD is high, reaching values up to 4. High is also the AOD anomaly with maximum values up to 4 again. Here we present the AOD and DOD geographical distributions for the same day, but this time using Meratory analysis data. As we can see, the patterns are quite similar with those taken from MODIS measurements. However, here we don't have white shaded areas because we don't have missing values. While we also have used different color bar because the values of AOD are now lower, varying from 0.1 up to 1.4. This is attributed to the underestimation of Meratory analysis when AOD become high. Here we present the AOD and DOD anomalies. Again, we have similarities with the anomaly distributions from MODIS data, but again we can see the lower values, which reaches 1.2. Here we present the cloud fraction distributions for liquid and ice clouds, as well as for their combination. And what we would like to highlight is that mixed phase clouds are formed over the dust export area. And specifically, the formed clouds are mainly ice ones. Here we present the geographical distribution of cloud top properties. As we can see, the formed clouds are middle to high ones with cloud top heights between 5 and 9 kilometers and cloud top temperatures between 240 and 270 Kelvin. And let's go to the vertical analysis. Here we present the cross-section across which we took the vertical distribution of dust optical depth and temperature gradient in order to investigate the possible connection of dust presence with the formation of temperature inversions. Here we present at the upper left figure the dust optical depth vertical distribution, and what we can see is that dust is injected in the atmosphere at two levels, one near the surface, which is observed over the source areas of northeastern Algeria and Tunisia, and an elevated one which is observed above Tunisian coasts, Tyrrhenian Sea, North Italy and Adriatic Sea, and extends from 2 to 6 kilometers above ground level. At the bottom right figure we can see the temperature gradient, and with red color we indicate the temperature inversions, while with white shaded areas we indicate the reduced temperature gradients. What we observe is that temperature inversions and the reduced temperature gradients are observed just below the elevated dust layer. Here we present the horizontal cross-sections of wind direction and speed, relative humidity, dust optical depth and temperature near the surface at 950 hectopascal, and what we observe is that maximum dust optical depth values are noted over the source areas of Algeria and Tunisia, where relative humidity is minimum and temperature is maximum. And here we give the same results, but at the level of 800 hectopascal, approximately 2 kilometers. And we can see again the maximum values over the source areas, but we can also see high values over the dust export area, where relative humidity is minimum and the temperature is maximum. And here we summarize some basic conclusions, but before we give them, I would like to highlight that these conclusions refer not only on the first episode day, which was presented in this presentation, but also on the next two episode days, namely 17 and 18 June 2016, which were also examined, but don't present it here due to the limitation of time. Well, a trough of low pressures over the eastern tropical Atlantic Ocean and the Iberian Peninsula and a ridge of high pressures over the western Mediterranean basin prevail one day before the episode and move eastward while the episode evolving. Mixed phase clouds are formed over the dusty area. These clouds are characterized as middle to high ones, with cloud top heights between 4 and 6 kilometers and cloud top temperatures between 240 and 280 Kelvin. Dust optical depth systematically exhibits two peaks, one near the surface and an elevated one between 4 and 6 kilometers. Slight temperature inversions or reduced temperature gradients are observed just below the dust layers, and the results of this study make evident the existence of significant effects of exported African dust on the Mediterranean cloud properties and atmospheric temperature structure. These effects are being studied for a large number of decades. Thank you very much for your attention.
Thank you very much, Maria. There are questions. Are there questions from participants? No. I don't see question in the chat bar. Okay. Maybe one question.
Thank you.
Yeah.
Are you able to explain why you observe temperature inversion just below the layer of mineral dust? I found this a very compelling and very interesting conclusion.
I'm sorry, but I couldn't hear the question.
Repeat.
May I explain?
The question was that you apparently observed from calculations a temperature inversion just below the cloud, the mineral dust layer. Could you explain this in terms of physical picture, why this is so?
Yes, of course. We know that dust aerosols absorb solar radiation, and they warm this heat this way the atmosphere, and thus the layer where they exist. Simultaneously, they cut a part of solar radiation which reaches the surface, and so the layers below the dust layer appears to be cooler, and the layer where dust exists is warmer. This causes the temperature inversion.
Okay, thank you, Maria. If there are no further questions, I can move with the next presentation of Larrasoaña, Juan, Cruz, and the presentation entitled Magnetic Characterization of Natural and Anthropogenic Atmospheric Deposition over Southwestern Europe, Results from the Donair Network.
Good morning to everyone. I am Juan Cruz Larrasoaña.
I'm sorry. Okay.
Good morning to everyone. I am Juan Cruz Larrasoaña. I'm going to present this study that has been conducted by a large team of people working in different Spanish institutions and also in Australia. And this has been done in the framework of this Donaire project and its continuation called the POSAPI. A brief outline of the talk. First, I will give a brief introduction on why magnetic properties of atmospheric deposition are important, why we started to work with this Donaire network, and then I will go through a short section of materials and methods. I will present after that the results and discussion, and I will conclude with just some sort of take-home message. Why magnetic properties of atmospheric deposition are important? But there are two main reasons. The first one is that magnetic minerals are ubiquitous in particulate matter. More specifically, it has been reported from a large number of studies in different places over the world that urban and industrial environments contain anthropogenic magnetite and mahimite, which are two minerals which are very similar in composition and magnetic properties. In addition to these anthropogenic magnetic minerals, hematite has been reported as a very, very common constituent of natural aeolian dust. The second reason why magnetic properties are important is because magnetic properties provide a rapid and inexpensive way of monitoring the amount of these minerals. And it has been shown in different studies that the amount of these minerals can be in turn be used as a proxy for either pollution or the flux of aeolian dust. There has been a great number of studies dealing with this topic, but there is an overall problem as we see it. First of all, most of the studies deal with mainly single sites. So it's difficult to extrapolate conclusions to larger areas. There is also a large variety of samples used to study atmospheric deposition. Sometimes air quality filters are used, sometimes tree leaves or bark are used as a passive collector of atmospheric deposition. Sometimes road dust is directly collected from the streets. And there is also a large variety in the collecting period which ranges between few days and a full days. And this also has variety on the impact that some anthropogenic hematite might have on these studies, and also in the possibility that magnetite and mahimite is not only anthropogenic, but it comes also associated with aeolian dust. So all these characteristics make somehow blur the interpretation that can be done from present day or papers that have been published up to now. So in order to cover this gap, we designed this donating network in which we included 15 sites typifying representative climatic and demographic settings across southwestern Europe. The study area ranges from a Mediterranean type of climate to Atlantic Ocean type of climate to continental climate in the interior of northeastern Spain. The sampling was done bi-weekly, simultaneously in all the different sites. And the monitoring period is a bit more than a full year. And this is important because it's a very homogeneous sort of sampling and study that can be extrapolated to other southwestern European regions where there is a clear, there is a problematic with pollution in industrial and urban areas, and it might be also a problem or necessity to separate this anthropogenic source of atmospheric deposition, to separate it with the natural counterpart or contribution, which is related to the arrival of North African dust from the south. Okay, going to the materials, I show here in the left corner of the image, in the lower part, a detail of one of these homemade collectors that we use for capturing the atmospheric deposition. It's just composed of a funnel, plastic funnel, which is collected through a pipe to a vessel, plastic vessel that is encased in one of these black boxes to prevent affection by light. And these collectors were deployed at the different sites when possible in stations aimed at monitoring air quality. And every second week we were going to the place, and we used distilled water to clean the funnel and to put all the material that was trapped in the funnel inside the bottle with all the material that had fallen previously, either as wet or dry deposition. Once we have these vessels, plastic vessels full of water with all the atmospheric deposition collected, we pumped this water through a coarse wool filter. And here in the lower part of the image, you have an example of some filters, and you can see already a significant variety of colorations depending on the amount and the type of atmospheric deposition collected. The methods that we use, first of all, we did a characterization of the magnetic minerals in selected samples, typifying different settings and atmospheric scenarios. We did a number of measurements. The most important ones are mentioned here. The first source of information was what we call the IRM acquisition curves, where the magnetization of the sample is measured as a function of intensity of a magnetic field where the samples are exposed to. And different magnetic minerals acquire most of the magnetization at different fields. So splitting the whole curve into different components, we can establish the different magnetic minerals present in the sample. All this information was backed up by series curves and fork diagrams. I won't go into details into that. And this information was combined with some observations on iron oxide particles. And once we had done this, what we did was to use information on these RM acquisition curves to apply specifically the magnetic fields to all the samples that were able to separate the different components. So we use this IRM at 0.3 Tesla as a proxy for magnetite mahimite abundances. They are very similar, magnetically. And then we use this hard IRM parameter, which is the IRM applied at 1.2 Tesla minus the IRM applied at 0.3 Tesla. And this can be used as a proxy for hematite abundances. Now we combine for all the data, for all the samples, this data with geochemical proxies for vehicular traffic and also for the supply of North African dust. Okay, I will go through the results now. Here I show the summary of the magnetic properties and same observations of samples typifying urban sites. Here we see a yellow curve, which is a fit to the results, which are the dark gray spots of this IRM acquisition curve, the derivative of this curve. And what you can see here is that this curve can be decomposed in three curves. The first one is attributed to component 1, this C1 in purple here, which we associated with coarse anthropogenic magnetite mahimite particles. You can see an example of very clear anthropogenic magnetite in this image. There is also a second component in blue called here C2, which we also associated with anthropogenic magnetite mahimite particles. These are irregular aggregates of iron oxide particles. And there is a third component composed of hematite, for which at this point no clear indication of its origin can be made. If we go to an industrial site, we see exactly the same components. This C1 attributed to large magnetite mahimite particles, this C2 attributed to these irregular aggregates of finer grains of magnetite mahimite, also of anthropogenic origin, and then this third component of hematite. If we go to natural and agricultural sites, we could get only reliable results for these curves in the case that atmospheric deposition was important due to the extra addition of North African dust. In this case, in addition to these C1 and C2 components associated to anthropogenic magnetite and hematite, we could see a component C3 associated to hematite and also a fourth component which is also associated to a different grain size or whatever of hematite. And in this case, we had enough material to provide clear proofs from the same images that this hematite was associated with other particles forming aggregates that are typical for aeolian dust. And what is important to notice also that in urban sites where there was some, in urban samples collected during a period of a significant North African dust breakout, we see exactly the same fourth components that we saw in the earlier case, with anthropogenic magnetite and mahimite and aeolian hematite. In this case, as you can see from this same image, in addition to these anthropogenic particles of magnetite and mahimite, signaled by a black arrow, we could observe single crystals of magnetite mahimite with the typical features of shown by detrital minerals, which in this case can be only aeolian. Here we show just an example for the Cantabrian Pyrenean region, where we compare in black on the left-hand side of the diagrams the hard IRM, which is a proxy for aeolian hematite. We compare this with the flux of aluminum, which is a proxy for North African dust. For this in black site, this urban site in Pamplona, and in green, these three natural background sites. And we see that the correlation between both parameters is quite good. And they signal clearly the two most important African outbreaks of African dust, which are signaled by these orange arrows. They are very clearly reported in both properties. And this indicates that this hematite is actually a good proxy for North African dust. If we do the same comparison between a proxy for anthropogenic, presumably anthropogenic magnetite and mahimite, this IRM at 0.3 Tesla, and we compare it with the flux of copper, which is a typical proxy for vehicular traffic, we see that the correlation is not as good as it was before in the previous slide. What is important to notice is also that some of the most important outbreaks of North African dust, marked here with this orange arrow, are associated with large peaks in the amount not only of magnetite and mahimite, but also in the amount of copper. And this raises the question of whether some of this magnetite and this copper is anthropogenic in origin, but blown from North Africa into Southern Europe during these Saharan dust outbreaks. In any case, the correlation between these two properties is not that good, probably because there is an addition of eolite and magnetite, and also maybe some pollution from North Africa. Anyway, to conclude, I want to tell you the main conclusion of the study, which, based on a combination of magnetic, geochemical, and SEM data from samples from the donated network, indicate that, first of all, magnetite and mahimite particles are of anthropogenic origin and were identified at all sites. We find evidence that some magnetite mahimite particles seem to be of Aeolian origin, which somehow weakens the use of these minerals as proxies for pollution, because there is this overlapping with Aeolian magnetite. And finally, we find evidence that hematite is of natural origin in all sites and represents a good proxy for the supply of North African dust. So the future scope for the new project is, in first place, to provide a full geochemical characterization of all the samples, and this way we can make a source apportionment of the different atmospheric deposition and separate the natural and anthropogenic contribution to this deposition, and also better calibrate the validity of magnetic properties as proxies for pollution and North African dust. And the other thing what we want to do is to apply these magnetic properties to longer time series and also to sediment cores to unravel in the case specifically of North African dust, the factors that modulate their arrival into Southern Europe, both in the present time and in the latest Holocene. And for those of you that want to have a more detailed discussion of the description of all the results, this has been published in a recent paper in Atmospheric Environment. And well, from my side, this is all. Thank you very much for your attention.
Thank you very much to you. Juan, are there any questions? I don't see a question for you. Thank you again.
Thank you.
And I think we can move with the 9th talk by Matthew Berg with his presentation entitled Studying Coarse Mode Dust Aerosol with Digital Holography from UAV. Yeah. Here, come here. Okay. No, I can see the presentation.
No.
Yes, but I have to start this presentation after the type. Oh, okay. It's so slow. Yeah.
Thank you very much. So if we think about characterizing aerosol particles, in particular large particles like the dust we've been talking about, in many cases we can't collect them. Sometimes we do, but sometimes we don't want to collect them, such as remote sensing or studies on aircraft and balloons. And this makes light scattering an ideal choice. And the basic idea of light scattering, of course, is you have some unknown particle and you illuminate it with a laser beam. And then you can take a detector and scan around an angle, collect a light scattering pattern. And then if you somehow properly interpret this pattern, the idea is you can extract things you'd like to know, such as size, shape, composition. Well, the problem is the following. Of course, it's the inverse problem. If you consider this light scattering pattern measured for an aerosol particle, you see it's a bunch of nested rings. And you might guess that this corresponds to a spherical particle. But what if you get a pattern like this? It's pretty much impossible to interpret this to extract anything meaningful out of the light scattering pattern. This is the essence of the inverse problem. Fortunately, there's an alternative to solve this problem, and that is digital holography. It's basically an direct imaging approach. So the way digital holography works is you perform two measurements. The first is you have an expanded laser beam illuminating a sensor, and you just record the beam profile. We call this a reference measurement, and it would look something like over here. See a broad Gaussian kind of profile. The next step is to allow a dust particle to enter the beam. And notice that it will scatter a little bit of the incident beam. And so there's two waves across the sensor. There's the scattered wave due to the particle and the unscattered wave, or the remainder of the illuminating beam. These interfere and create a fringe pattern on the sensor. So this fringe pattern is a hologram. Then you subtract the no particle measurement from the particle measurement to get what we call a contrast hologram. And the point of doing this is to basically remove background noise, and it improves the image you're going to get next. So how do we get an image of the particle from that interference pattern? The idea is basically diffraction. So if you look at this diagram here, on the left side, we've got the measurement configuration and incident wave coming in, illuminating a particle, scattered and incident light interfering on our sensor. Then we evaluate the Fresnel diffraction integral of this interference pattern recorded on the sensor, and that's basically simulating the diffraction process to form an image of the particle in this image plane over here. So here's an example of how well this works. This is a contrast hologram for pollen particles on a piece of glass. And when you apply the Fresnel diffraction integral to this interference pattern, you see very nicely resolved images of the individual pollen grains. Because it was on glass, we could take this sample and look at it under a microscope and validate that indeed we are producing the accurate image of this particular particle. You can see here that the image resolution is a few microns and that we're mainly looking at quite large particles here. Okay, but it could potentially be appropriate for dust studies. Of course, we want to do this on flowing aerosols, not particles stuck to a piece of glass. So the way we did that is we created an aerosol sample, draw the particles down out of a nozzle, and they pass through the intersection of two different colored laser beams here. You can see a picture of that over here. When the particles pass through that intersection, they scatter both colors of light simultaneously. This provides a coincidence signal for us to then cue a pulse from a red laser, comes down, illuminates the free-flowing particle. Again, you get scattered and unscattered light on your sensor, and hence record a hologram of these flowing particles. Here are examples of images of free-flowing aerosol particles taken from the holograms. In this case, we have two spherical glass particles, which we just use for calibration purposes. Pecan pollen aerosol particle, titanium dioxide particle, and then our old friend the ragweed particles. So it works fairly well, and you can get a good sense of the geometry and size of these objects. Another great advantage of holography is what I call long working distance capability, and basically it goes like this. You have a single laser pulse, expanded laser beam, and it's going to illuminate
particles on two windows. The first window at location 1 with a particle there, and then the second window at location 3 over here with a particle there. And these particles are of different type or nature. You both scatter a single hologram on your sensor over here, and just by changing the location of the plane that you bring particles on glass window number 1 into focus here, or window number 3 into here. And this is all coming from a single hologram exposure. And if you happen to choose an intermediate region, say here in 2, you get defocused images because there's no particles there. And the key thing here is this distance is about 4 centimeters, or on that order. So you don't have to focus lenses or even know where your particles are. They pretty much anywhere in this depth of field or focus, and you can bring them into focus. So we use it to get images of
We can move with the last presentation of this slot with Monika Ogrizek, that will present her work entitled Green Method for Determination of Metal Content in PM Deposited on Quartz Fiber Filter, LA-ECPMS.
Hello, my name is Monika Ogrizek and I'm a PhD student at National Institute of Chemistry, Slovenia. I'm going to present a new laser ablation ICP-MS method for determination of metal content in PM deposited on quartz fiber filters. Particulate matter, or PM, are particles suspended in the air. PM are next to volatile organic compounds and greenhouse gases considered as air pollutants. They can origin from natural sources like sand, particles from volcano eruptions, or natural occurring wildfires, or from anthropogenic sources, for example from industry, traffic, or some combustion processes like heating of homes. And after PM is released in the air, it can hover there for a longer period of time and even get transported at long distances, as we know, for example, from Saharan dust events in Europe. But eventually the PM are deposited to the Earth's surface, where we can breathe it, or it can have some toxic effect on vegetation or the environment. PM represents a very diverse group of particles, which depends on their source. They may contain inorganic compounds, as are crustal elements from the Earth's crust, ions, elemental carbon from the combustion processes, and trace elements. Organic compounds are mostly organic carbon. The size of PM is also dependent on its source, and it's from a few nanometers at soot to some micrometers, as are pollen or Saharan dust. The PM10 is the label for particles smaller than 10 micrometers, and PM2.5 are particles smaller than 2.5 micrometers. So the number represents the cutoff size of the particle diameter. And why is PM so important? Because it has negative effect on many different levels and is considered one of the most dangerous air pollutants. It could affect the environment by disrupting solar radiation balance and consequently causes heating of the atmosphere. It can also influence the ecosystem. For example, it can be deposited on the vegetation surfaces or dissolved in the water and then change the nutrient balance or the availability of the elements. It could also influence the cultural heritage. For example, this black crust on the churches or some historic buildings is due to PM, and this can disturb and contribute to stone damaging processes. And last, it can have negative effect on health. The inhalation can cause pulmonary or cardiovascular diseases, which can be caused by particles itself or by some toxic components inside the particles, as are arsenium or cadmium. And fine particles with diameter smaller than 2.5 micrometers are more harmful because they can enter the bloodstream through the lungs and travel around the body. Therefore, PM and some components are already regulated in European directives, and also the monitoring conditions and standard methods are prescribed. So, PM is most commonly sampled by PM sampler. So we put in a blank filter. Here's an example for quartz fiber filter. And then the air is drawn through the sampling head, where we choose the size of the PM that we want, for example PM10 or PM2.5. And then particles get deposited on the filter, and the result is a loaded filter, where then many different analytes are normally measured, as they're listed here. And in Slovenia, the agency responsible for air monitoring is ARSO. This is Slovenian Environment Agency, and they monitor many different compounds, as are metals, Pah ions, elemental carbon, organic carbon, and they monitor it on the same sample, which is collected on daily basis. There are other filter metrics alternative, but quartz fiber filter is the only possible filter metrics for OCEC determination, and that's why we also choose to develop a method on quartz fiber filters. And in the European Union, monitoring agency normally use the prescribed standard method, which is the 14902. And this method uses microwave digestion ICP-MS for its determination. In the European Union, there are some regulations and directives concerning air pollution. And here I would just like to point out the standard method for elements that I already mentioned before. This is 14902, and it is certified only for 4 elements listed here. But in the directives, the monitoring of some other elements are also required, as are, for example, chromium, selenium, zinc, and the standard method for those elements does not exist yet. And this is one of the problems that I would just like to point out. So this standard method for determination of lead, cadmium, arsenic and nickel in suspended PM prescribed sampling with PM sampler. Then a small subsample is taken from a sample and digested with the use of microwaves and concentrated acids. So the sample in a liquid form is obtained, and this sample is then analyzed by ICP-MS. The problem with this method is a microwave digestion pre-treatment step, because it uses concentrated acids, which consequently ends up as toxic waste, and because it is standardized only for 4 elements. This is presumably because for other elements, digestion efficiency are not sufficient for all PM compositions, and it is also a time-consuming step. To avoid those problems, we developed a method with laser ablation ICP-MS, where instead of microwave digestion, we use laser ablation, which can use a solid sample and is directly coupled to ICP-MS. So how does laser ablation works? we put a sample in the ablation cell, and the laser head produces a laser beam, which ablates the sample, producing some aerosolized particles, which are then transported with argon or helium gas to the ICP-MS. So with laser ablation, instead of microwave digestion, we can use solid sample, so no pre-treatment step is needed, and consequently we don't have any toxic waste. We can have multi-element determination because we don't need to worry about the digestion efficiency, and we can also obtain lower LODs and require less sample for the analysis. And here I would just like to take you briefly through the method development steps. First, we did a parameter optimization, and we chose 3 parameters based on our educated guesses. The beam size, we chose the biggest beam size our laser ablation system is capable to produce, simply because if you're doing a bulk analysis on an area, it is faster if you use larger beam size. And then we optimize the fluence. This is simply the energy of the laser. And we tested fluence from 0.5 to 4. And we can see here that at fluence 0.5 the signal is a little lower because not all of the PM was ablated. So for the optimal parameter we chose to be fluence 1.5 because above that fluence the signal stays the same. And another reason is that because at higher fluences some shredding of the filter occur, which could cause some problems in the instrument. And the next thing was the optimization of the dosage, and this parameter is how many times the laser fires or ablates on the same area, on the same spot. And we can see here that with dosages, small dosages, 1 to 3, not all the particles are ablated, and from the dosage 10 above, the signal reaches a plateau. So above the dosage 10, all the particles are ablated for the filter. That's why we chose 10 overlaps for sufficient dosage for ablating all the material. And we tried this on high loaded filter and low loaded filter, so the method would be robust enough for the winter samples where we expect higher concentration, and the summer samples when usually we have lower concentrations. The second thing we needed to assess was the blank filter, the filter without any PM deposited on, simply to see if the blank filter contributes to this measured signal. And the instrument has some background that is called gas blank. This is the background that is just from measuring gas flowing through the instrument without any ablation. And this is the green one. And then when we ablated the blank filter, this is the gray one, we compare those signals for every element to see if there is any difference. And as we can see here, mostly there is no difference between those signals, so there is no contribution from filter blank to the measured PM concentrations. In the next step, we wanted to determine a subsampling procedure, so we need to look into the homogeneity of the samples. And first we assess the influence of location on the filter to see if there is any difference in the position of elements between the edge or the center of the filter. So we ablated a few lines from the edge to the center, and as we can see here in the plotted signal, there was no trend observed in the ablation signal, and we concluded that there is no difference between sampling at the edge or in the center of the filter. However, we did find some strange spike randomly appearing through the measurement, which will be discussed in the later step. Next, we wanted to determine the smallest subsample size that would still be representative for the whole filter. First, we ablated a large area of the filter and find some large spikes which represent less than 1% of total number of pixels, but largely contribute to variability between the pixels, but does not drastically change the average of the samples. And because we wanted to know what is the average of the whole filter based on measuring only a small subsample, and in a small subsample the spike could have much larger weight than other pixels, we concluded that for this method it is necessary to remove spikes before the analysis. Here I would just like to show a representation of statistical analysis. So if this is our large ablated area, first we calculated the average of the whole area. This was a sample average. And then we divided the sample to units. And the value of every unit is the average of covering pixels. And then we took 3 random units. This was the subsample, and calculated its average and 95% confidence interval. And we repeat this for every possible triads and count how many triads contain the sample average in its 95% confidence interval. And if more than 95% of triads were appropriate, the size of the subsample was considered as sufficient. And we conducted the analysis on different unit sizes, on smaller and smaller. And here we can see the results for all measured elements. And we can see that with the decreasing of subsample size, the number of representative subsamples also decreases. And since we set the limit to 95%, the smallest representative subsample size was 3 randomly chosen units with 12 square millimeter size. The next step was the calibration of the results. The problem here was that laser ablation ICP-MS needs a matrix match standard for calibration, and that commercially available standard that would be PM on quartz fiber filters with certified elemental composition does not exist yet. Therefore, we used custom-made standard, and we took 3 real-life samples and measure its elemental composition by absolute method of INAA, Instrumental Nuclear Activation Analysis. And so we got the information on elemental composition. So we could use those samples as standard and quantify some other samples measured by laser ablation ICP-MS based on those results. As a final step, we compared the results from newly developed laser ablation ICP-MS method to absolute method INAA and standard method microwave digestion ICP-MS. Every triangle represents 1 element, and the 3 methods are placed 1 on each axis. The stars in the corners represent the statistically significant difference between the methods. Here we need to keep in mind that laser ablation ICP-MS and INAA are not totally independent, since laser ablation was calibrated based on INAA results. More interesting fact is that there is significant difference between microwave digestion ICP-MS standard method and laser ablation ICP-MS and INAA in 3 elements: arsenic, iron, and vanadium. And this result confirms that ICP-MS with microwave digestion could have questionable recovery rates because of this microwave digestion pretreatment, and that laser ablation ICP-MS is a better method for determination of the elements. And in the last slide, I would just like to summarize the presentation. And here on the right is the protocol for the developed method. The method does not need any sample preparation, is more precise measurement and has lower LOD than standard method. It can determine more elements, uses less samples for the analysis, and does not produce any toxic waste during the analysis. And if anyone is more interested in the method, they can take a look at the recently published article in Talanta. And thank you for your attention.
Thank you, Monica. Are there any questions? In short, but I don't see a question. Okay. Monica, thank you for your participation in this session. If there are no questions, I think I can close also this second slot of presentation of this session for the lunch break. The third and last slot of presentation will start at half past 2 p.m. with Rosa Caggiano. Thanks a lot to you again for your participation and for high quality contribution to our session. Have a good lunch.